Hello everyone, welcome back. In this lecture we're going to be discussing about timing in digital circuits. Okay, timing is the most important when we discuss about how to design digital circuits. If your timing is not right, things won't work. If you don't fix timing violations or don't pay attention in detail, your chip may screw up, it may not work. So pay attention. This is the most important. This figure shows a very basic digital circuit. We talk about synchronous design. We discussed it in previous lectures. So modern systems are based on synchronous design. You may have asynchronous elements. So essentially, in synchronous design, what it is that that you have your logic flows between register to register, okay, or flops in general. And what the flops do, they store the state of your circuit, okay, and that state can be used, or in general is used on the when the next clock arrives, or next clock edge. Okay, so it is very important that the timing should work, that how much delay it's gonna take to do computation and produce the result and creates a valid state of the digital system. And then by the time next clock comes, all our computation should be ready to utilize that computational results in the next clock cycle. Okay, so every flop is associated with clock to Q delay. What is clock to Q delay? It is very simple, that it is the time from the clock edge, okay, and till the flop produces the output Q. In short, clock to Q. You have given some input at the D pin of the flop and you are expecting some output at the Q pin of the flop. Okay, so flip-flop gonna take some time to give you the output at the Q pin. Okay, and we take that delay from the clock edge and call it TCQ. All right. In the same way, your combinatorial logic will have some delay. So in short, we call it propagational delay, means how much time it takes to propagate logic from the Q pin of the first flop, okay, to the D pin of the second flop. So that's propagational delay, logic propagational delay. Okay, and every flop is associated with some delay called setup and hold. Okay, or setup window time for flip-flop and hold window time for flip-flop. And there is some delay associated with the clock, because you think that you will expect the clock at the C pin at the perfect time, right? Say at this time you want to see the clock, but do you think that at the proper time in every clock cycle the clock will arrive, or your clock generator, which is typically a digital PLL, is perfect enough to give you the clock at the right time? So there is some uncertainty associated with the clock. And there is another parameter, skew. Okay, so that is a clock edge variation between two different sides of the clock. Okay, so what it means that how much is the variation? The clock is coming at this source flop and the clock is going to this destination flop. So ideally we expect the clock to have arrive at the same T1 time and same T1 time at the second flop, but in reality it may not have. So it may have, say, T2 time, okay, and that causes the skew, or that's in short is the skew. And why it is so? Because you see, in whole chip how the clock is distributed. It's a big clock network. Say this is the clock buffer feeding to, it has say tons of branches, okay, and those going to different parts on chip. And due to one reason, you may call it, okay, the propagational delay of the clock circuitry, and also some due to manufacturing, okay. So I don't want to complete this whole circuitry. You may look in textbook the clock distribution network, okay. So we have say different delays associated, and also we do have say clock period. So how to constrain, okay, or what are the equations which will tell that, okay, how much should be your clock period, which can satisfy all these delay requirements, okay. So let's try to understand first what is the setup and hold time, okay. So every flip-flop has a setup time. What does it mean? That say if your D input is changing in this window, then your system will not work. It will latch the wrong state. So your input should be stable within this window, okay. So if it has to change, it should change before the setup window. But setup window is nothing but some time before the actual rising edge of the clock. All right. In the same way, there is a hold window. So what it means that your input, okay, coming to the flop, it should not change its state in this window. If it changes, it will not work. So what essentially it is, it should change the state after this window, okay. So it should satisfy or it should have some margin, okay. Let me put it in simple way, some margin before and after the rising edge of the clock, okay, at which you are trying to base your timing equation. So that's very simple. In simple words, some timing margin associated with each flop. All right, so that's setup and hold time. Good. Now let's talk about jitter. So jitter is something that you expect the clock to come in each clock cycle, okay, at the same time, t, let's call it t. But what happens that the clock may have some uncertainty, so it may come sometime earlier, okay, t tick, or it may come in next clock cycle sometime late. So some uncertainty, okay. We are talking about at the same flip-flops input edge, okay. So remember we had our circuit where the flop 1 is connected via some combinatorial logic with flop 2, okay. So we are talking about the same flop, okay. So that's the jitter, uncertainty. Now in the same way, the clock is associated with another uncertainty called skew. So what essentially skew is that let's say this is your first flop, this is second flop, okay. So now say you expect in the same clock cycle the clock will arrive here at t1 time, and at the same time it should go to the another flop, but it doesn't happen in practice, and that's why we get this we define this parameter which is called skew parameter, and that comes because of manufacturing defects, that it doesn't come at the same time we expect for the second flop, but some other time, say T1 tick. So that's a basic difference in skew and jitter. Okay. And now let's talk about the clock to queue. So as we said earlier, this is nothing but how much time it takes to produce the output. So if your D is like this, is changing from 0 to 1, okay. So how much time is going to take from the clock edge to get the output at the Q pin, that is TCQ, for each flop 1 and 2. All right. Now let's talk about the equation for the setup time. Okay. So what essentially this equation means that so we have the clock period, T clock is the clock period, okay, one clock period, and all the computation has to be done within this period. But since we have jitter, okay, since we have jitter with each clock edge, okay, and as if you remember the previous drawing, we have 2 flip-flops, okay. So the jitter will be associated with each clock pin, okay, or for each flip-flops clock pin. So you have to multiply it by 2, and you are subtracting, means that your available time for computation would be less than T clock. Let's say that much is the only available time you have because you have jitter. So T clock minus twice the jitter, this is your available time for the computation. It should be greater than and equal to clock to Q delay plus propagation delay, the delay for your logic to propagate from the Q pin of the first flop to the D pin of the input flop, okay, plus the setup time and plus the skew. Okay, setup time means that your, as we discussed, this time window, and the skew. Let's say if we are talking about this flop, so we get some skew in the clock. So that equation must be satisfied for the setup time constraint. All right. In the same way, let's talk about the hold time constraint. The hold time constraint is simply saying that our the input to the flop, okay, should not change in this window. So what essentially means that so clock to Q, we had, remember this drawing, we have these 2 flip-flops. So clock to Q delay, okay, and plus this propagation delay, and minus the skew at this edge, okay, minus the skew, and twice the jitter, okay, that should be greater than hold. I mean, this total time, okay, should be bigger than the hold window for the flop. Okay. So that equation must also have to be satisfied. Now you may have say you may have hold violations. So what are you going to do with the hold violations? So essentially what we are trying to do is the delay in this path and delay in this propagational path, okay, should be greater than the hold window of the flop. Should not. So let's say T1 TCQ plus TP, okay, and your signal is propagating and it should not change in this whole window. So it should be stable, and then it should change if it is changing at all. So if it is changing in between, let's say if it is changing in between here, then what is the job here is to increase the delay. And how can you increase? Well, simply insert the buffers in the path. Okay, simply insert the buffers so that this delay is more. Okay, so you are basically increasing the propagational delay. Now if you insert the buffers, it may disturb the setup time requirement. Okay, so it's basically essentially it's sort of thing that you got to play around. Once you have nowadays there are EDA CAD tools. Say PrimeTime is industry standard tool which does the time checks for your digital design. So you take out the each path, okay, wherever you see the timing violation, and if you see the whole violation, you can try to insert the buffers in that path and run the session again for both the setup and hold time till you get both times correct. All right. So these are two important equations for setup and hold time, and these two must satisfy, your design must satisfy. Now if you have setup violations, okay, so setup violations essentially means that well, you got to adjust your clock. Okay, for the hold violations you can get away, inserting the flops, you can fix it up. But for setup violations you have to check, you have to increase the flop, or you have to basically do things which are associated with the clock path. So in short, the setup violations or setup is associated with the clock and hold is associated with the data. So clock path, setup, data path, hold in short form. Okay. So thank you very much guys for listening me and enjoying the lectures on Lee Professor YouTube channel. I welcome your comments, and if you need some other lectures for other subjects, please feel free to send me a message. Once again, thank you for subscribing, and those who have not subscribed, please do so. We appreciate your feedback and support.